These composite panels represent the computation of topological markers for an aperiodic quasicrystal containing over 268 million sites. A C10 symmetric map emerges, where Chern markers quantize into red and blue domains, mirrored in the local density of states supporting the system's topological order. While standard quantum models are typically limited to a few hundred atoms, this algorithm bridges the gap to the macroscopic regime, handling a network of 268 million sites. Calculating exact local topological invariance at this scale was long considered computationally intractable for non-periodic systems. The challenge lies in the structure itself. Because a quasicrystal is non-periodic, it lacks the symmetry-based shortcuts used to simulate standard crystals, requiring a massive increase in computational resources. Successfully mapping this 268 million site problem provides a pathway through a major computational wall in condensed matter physics. Standard simulations of macroscopic materials rely on periodic boundary conditions to manage data. This is the domain of Bloch's theorem. It exploits translational symmetry to reduce the analysis of a macroscopic solid to the study of a single repeating unit cell. Quasicrystals, like this Penrose tiling, break this assumption. They possess deterministic orientational order, but lack periodic translational symmetry. Their stability relies on matching rules, where unit cells like these fat and skinny ROMs pack together without ever repeating exactly. Because the structure is aperiodic, Bloch's theorem is invalid. A standard Bloch wave cannot propagate through this geometry without fracturing. Without a repeating unit cell to act as a shortcut, researchers must directly compute the entire macroscopic lattice to understand its electronic behavior. This creates a memory crisis. Attempting exact diagonalization for a million-site dense matrix leads to an explosion of the Hilbert space that exceeds the capacity of standard supercomputers. Overcoming this requires a mathematical framework that can calculate thermodynamic and topological properties without relying on translational symmetry. To bypass the limits of standard diagonalization, researchers turn to tensor networks, a family of algorithms borrowed from the field of quantum computing. The process starts with a 2D real-space tight binding model, representing electron interactions across the macroscopic lattice. The algorithm maps these 2D sites into an auxiliary one-dimensional many-body pseudospin chain. Data organizes along this chain via an index transformation, defining each site's state. This mapping allows the algorithm to process the system's information without ever having to explicitly store the full massive Hamiltonian matrix in memory. This dimensional shift transforms an intractable geometric problem into a solvable many-body data structure. The Hamiltonian for this tight binding system is constructed using standard fermionic operators. This Hamiltonian is then reinterpreted and compressed into a matrix product operator, or MPO, format across the pseudospin chain. By applying a kernel polynomial method to this architecture, the algorithm can efficiently handle the dense matrices that characterize these large systems. The density matrix is subsequently calculated and reconstructed entirely within this compressed tensor state. In this form, the memory required to represent the density matrix scales only logarithmically with the size of the system. This MPO framework resolves the scaling issues that previously limited direct quantum simulations to systems of a few thousand sites. Calculating the local topological marker requires the application of spatial position operators, x-hat and y-hat, to the compressed matrix. But standard multiplication causes tensor bond dimensions to explode, leading to a computational error state. The solution is the quenched position operator, dynamically centered relative to the specific calculation site. Using a small angle approximation, the algorithm bounds the position operator to suppress bond growth. By limiting the value of lambda, it captures the local environment without allowing data expansion at the edges. This targeted approximation is the final key that allows the algorithm to safely compute topological invariance across millions of sites. This optimized algorithm was applied to a real-space pi-flux model to test its precision. Researchers injected a C8 symmetric modulation into the lattice, visible here in red. The resulting output maps the local Chern marker across the entire system. This reveals a Chern mosaic, where the local Chern numbers strictly quantize into highly organized topological domains with sharp boundaries. These mathematical domains physically alter the material, as seen in the corresponding local density of states. Because of the aperiodic geometry, these domains self-organize without the need for periodic repetition. These results demonstrate that quasicrystals host strictly defined, repeating local environments even at macroscopic scales. The true physical value of these massive churn mosaics is found exactly at the boundaries separating the different topological domains. These boundaries host protected in-gap edge states, unconventional quantum excitations that facilitate conduction. Electrons propagate seamlessly along these topological boundaries. Because these edge states form a continuous network, they shield electrical transport from local scattering or structural defects. This provides a level of protection against noise and interference that standard conductive materials cannot match. This allows for the design of aperiodic structures that can represent, encode, and transfer quantum information with minimal loss. By applying tensor network methods to these macroscopic models, researchers have confirmed that bypassing Bloch's theorem provides a precise blueprint for noise-resistant quantum architectures.